One of the main concepts of this chapter was our discussion of how to calculate a moment, which is a product of two vectors, one vector being a force vector and the other vector being a position vector or a distance vector. A special subset of a moment is what they refer to as a couple, or as the book might call it, a moment created by a couple. And what a couple is two equal and opposite forces separated by some distance, which creates a moment, again, just as we've seen before. And that moment is a vector which acts in a direction that'll be perpendicular to the plane of the two forces. So what you see here in their little diagrams are, again, two equal and opposite forces. In the middle diagram, you can see that the forces, like the point of application at A and B, are separated by a position vector that we could call R. Okay, so really the moment created by by a couple in this plane could be viewed as the product, or the vector product, of the position vector R multiplied by the force vector F. Okay, so we can look at this much in the same way that we've looked at moments earlier in this chapter, and the calculation of moments as being a cross product earlier in this chapter. Again, the cross product idea is very, very good for when you have three-dimensional problems, and it's actually a simplification to the three-dimensional problem when you try to calculate moments. In two dimensions, this again, the whole idea of cross products and whatnot, it can be used, but it's not really needed, because in two dimensions what you can see there is what we are interested in is the not so much the direction of the moment, but we're interested in the magnitude of the moment. And in that case, in two dimensions, this just breaks down to force times distance r. Now again, you'll see r times f times sine theta, except that will maximize itself at an angle of 90 degrees, or when the distance between the two force vectors is perpendicular. Okay, so if we're using a perpendicular distance, this is basically going to break down in two dimensions to the moment of the couple being a force times the distance between the forces. And that's most of the time what we're really interested in is what is the the magnitude and the maximum magnitude of the couple. Again, just like what we said earlier, and this is down in the third drawing on this slide, that we said earlier that really when we're talking about moments, we're talking about the production of a vector that will reside perpendicular to a plane. So the couple, the forces, are in some plane. It can be an X, Y, or Z plane, or it can be some other plane. Doesn't really matter. But the moment, again, will be coming perpendicular out of that plane. And the direction of the moment can always be found by, again, that right-hand rule. So if you can imagine, the position vector down, or the position distance, I guess you could say, down there is d, and if we could rotate, through an angle, like turning d to the force that's labeled negative F, you could see your thumb sort of pointing up or out, coming out of that plane, and that would actually be the moment vector. Okay. Again, you can have two couples with equal moments in a number of different ways. I mean, up there they're saying F1 times D1 equals F2 times D2. I mean, this is an important idea, but it's an idea that's pretty straightforward. You know, if I had a force of 100 pounds, you know, if I had force vectors of 100 pounds going opposite, and I had 10 inches between them in a scalar type fashion, I could say 100 pounds times 10 inches, and I could get 1,000 inch-pounds. Okay, how else in that same plane could I produce 1,000 inch-pounds of moment? In this case, if you're looking at those pictures going in a sort of a counterclockwise direction, well, I could do it a number of different ways. I mean, what if I had my forces be 200 pounds? Then how far would they have to be apart? They'd have to be 5 inches apart, because 200 pounds times 5 inches produces the same moment of 1,000 inch-pounds. Okay? I mean, we could go through this. 250 pounds times 4 inches, again 1,000 inch-pounds. So, I mean, truly within the context of a given plane or a given problem, you could even say, you can have a number of different types of or a number of different couples that will produce the equivalent moment. So again, this is what they're saying here. The addition of couples, they're showing you this slide. What they're really trying to get at here is they're showing two intersecting planes, and they're showing couples being developed. They're showing you like an F1 and a negative F1 separated by a position vector, or you could say a distance R. Okay, and then they're showing you F2 and negative F2 separated by the same distance vector R. Those again produce, those are couples, and they produce a moment in each one of those planes. Okay, now imagine, if you will, sort of that horizontal plane, where F1 and negative F1 are located in. Again, if you could use that right-hand rule, all right, where would your moment vector actually be drawn? Your moment vector in that case would actually be drawn like coming out of that plane. Now, for a minute, if you can imagine the F2 vector, and if you think about how that is actually being positioned, it's creating a moment vector in a different direction. But if you think about what we talked about earlier, is, hey, if I want a cross product of vectors, I mean, what that actually forms is a parallelogram, and in this case, the resultant moment would simply be the addition of those two cross products. So again, what the long and short of it is this: in this case, in cases with couples of moments, you can just simply add them together, and that's pretty straightforward. This slide, again, the biggest thing here is that again, when you're dealing with a couple, you're dealing with a moment. So I mean, you can have a moment vector in some plane, not necessarily the plane that's the XY plane or the XZ plane or the YZ plane. You can have it in some other plane, and that couple, the moment produced by that couple, is not restricted to a particular point. It's called a free vector. And what they're showing there at the end, and we already know this, is we can take any vector that might not be purely in the, like I say, the XY plane or the YZ plane. We can take any vector like that and we can resolve it into an X moment, a Y moment, and a Z moment. So again, with couples, the actual point of application is not really all that important because they're free vectors. What is important is the concept of the magnitude of the moment and the direction of the moment. Okay? And that's what really, as you go across from the first illustration to the second illustration to the third illustration and the fourth illustration, that's what they're trying to get at. You've got a couple, the moment produced by that couple acts perpendicular to a plane, but again, the point of application is really not all that important, and we can take that moment and we can break it down, resolve it into X's, Y's, and Z's, just like we take a force and be able to break that down into X's, Y's, and Z's. This slide right here, what they're talking about in here is that, sometimes when we're trying to come up with, and you'll see this in some of the problems that we work, when we're trying to come up with equivalent systems, an equivalent system is a system that does the same thing as the original system. Okay, so in that first slide right there, you've got a force and you've got a position vector r. So that body, that rigid body, is acted upon by a force F and some moment that is occurring about point O. All right. Sometimes it becomes advantageous to us to think about, that original situation is a situation instead where the body is still acted upon by force F, but it's acted upon by force F in a moment, and in this case it'd be a couple. And so how do we do that? Well, what we do is we basically create, sort of a fictitious couple by putting two forces, an F force and a negative F force, down there at point O. Now when you do that, again, translationally, you're not doing anything to this body. If this body's out there in space and it was being pulled on by force F, the addition of F, another F, and a negative F at point O does nothing. Okay, there's no net effect by doing that. Okay, but how we can look at that then is if we take the force F at point O, you can see the negative F and the original F form a couple. Okay, so again, from the left-hand illustration to the right-hand illustration, we can take that original system over there on the left and we can again resolve it or create an equivalent system as shown over there on the right. And again, sometimes that'll be advantageous for us when we do this. All right, so they're just basically showing you that concept there. There's another one similar to this where we could again resolve a force into a force and a couple, and this time it can be at a different point. The long and the short of it here is if we're going to use a different point, what will ultimately happen is, we are going to move the force F ultimately to a new point. They're calling this point O prime. The real difference in here is that the moment created, and they're calling this moment O prime, really has to be the addition of what would have been the original moment created about point O plus the new moment, because now force F is a certain distance away from point O. So again, we can do something that's similar to what we did in the past. We can move it to some new arbitrary point they're calling point O prime. The big difference here, though, is the moment, the new moment that's created about this point O prime has to be the moment from the original point O plus, you know, the new moment created relative to that point O.